Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on December 5th, 2025, about a week ago. It shows that with the right hyperparameter transfer rules, matrix-preconditioned optimizers like Muon and Shampoo can train large language models about 1.4 times and 1.3 times faster than AdamW, and these gains stay consistent from 190 million up to 1.4 billion parameters. The paper is titled, Hyperparameter Transfer Enables Consistent Gains of Matrix-Preconditioned Optimizers Across Scales. And as we will see later, the implications for reliable optimizer benchmarking are quite significant. Alright, Figure 1 gives the big picture that motivated the whole study. The left block of panels shows that with the maximal update parameterization, the loss curves across different widths align and improve smoothly, while the standard parameterization causes unstable learning rates that either diverge or underperform. The bottom left panels over training steps highlight that wider models consistently help once the scaling rule is applied. The top right plot compares loss versus compute, where Muon and Shampoo stay clearly below AdamW when paired with maximal update parameterization and 1 over width weight decay. The bottom right plot then translates this into compute multipliers, showing roughly 1.4 times and 1.3 times efficiency gains that collapse when the standard parameterization is used. So Figure 1 contrasted overall performance, and Table 1 now spells out the exact scaling rules that make those gains transfer across model sizes. The table lists Shampoo, Soap, Muon, AdamW, and grafted optimizers, and for each one it gives how the effective learning rate should depend on input and output dimensions, depth, and block sizes. These formulas tell practitioners how to rescale a base learning rate when width, depth, or blocking change, so feature learning stays consistent. The final column shows that for grafting, the correct rule is simply to reuse the learning rate from the base optimizer Q1. Well, Figure 2 tests whether those scaling rules actually transfer learning rates across widths. The top panels compare standard parameterization to maximal update parameterization, and the U-shaped curves stay aligned across widths only in the maximal update parameterization row. The lower left plots show that, under maximal update parameterization, a single learning rate chosen at width 128 gives low loss, even when width grows to 4000. The bottom right plots track the root mean square feature change, confirming the coordinate check for all optimizers, except Soap, which already hints at its later failure. Alright, Figure 3 digs into how to fix the late training issues that Figure 2 revealed. The full grid of plots shows that adding either blocking or explicit normalization stabilizes where the best learning rate sits as width grows. The left block of panels demonstrates that using a block size of 128 keeps loss versus learning rate nicely U-shaped across widths for Shampoo, grafted Shampoo, and Soap. The right block of panels shows that spectral normalization, labeled norm, similarly tames the drift in both loss and root mean square feature change for these optimizers. So while Figure 3 focused on width scaling fixes, Figure 4 demonstrates that the same optimizers also transfer cleanly across depth. The top grid compares standard parameterization with alpha equals 0 to the 1 over L residual scaling with alpha equals 1, and the lower losses consistently favor alpha equals 1. The bottom grid's plot loss and root mean square feature change versus depth, showing that alpha equals 1 keeps both metrics smoothly controlled even as transformers grow from 3 to 192 layers. So while Figure 4 dealt with depth, Figure 5 shifts to the compute optimal setting and asks how learning rate and weight decay should scale with width. The left panels show that maximal update parameterization, and especially spectral normalization, keep the loss versus learning rate curves aligned across widths so a single base learning rate stays near optimal. The right panels plot loss versus rescaled weight decay, and the minima line up when weight decay scales like 1 over width across Muon, Shampoo, and Soap. Okay, Figure 6 translates those scaling rules into real compute gains. The left panel shows that, as model size grows from 190 million to 1.4 billion parameters, Muon and Shampoo match or beat AdamW on loss for the same compute. The middle panel converts this into compute multipliers, where correct maximal update parameterization plus 1 over width weight decay keeps Muon near 1.4 times and Shampoo near 1.3 times faster. The right panel demonstrates that partial or standard scaling steadily erodes Muon's advantage, eventually dropping its multiplier below 1. So the two big takeaways are, first, matrix-preconditioned optimizers like Muon and Shampoo really do deliver consistent 1.3 to 1.4 times compute savings, as long as learning rate and weight decay are scaled correctly. Second, Reliable optimizer comparisons basically require such hyperparameter transfer rules. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.